Semester, okay. It's been difficult time, so hope you guys still hanging there. And our final exam is going to be next Friday or Friday next week, May the 1st. And I've decided to do from 12 to 6 p.m. This is exactly the same time frame of your master exam is going to be, either in application or in theory. You have 6 hours to working on 3 problems each, okay? So master exam in application using online as well, but we haven't decided yet. We will make an announcement later on. Okay, but the reason for that is I wanted to get you guys to used to this kind of online formation. You need to do your best, either working on a paper or working on the electronic version of the writing itself. By any means is you need to learn how to producing eventually electronic file to upload. Okay, so then okay, so we are going to have 2 review sections. Okay, the first review section would be next Monday from 12 to 2. So keep in mind it's from 12. So we used to have 12:15 as a discussion section, but because I don't think you guys will have class anymore next week, so I'm going to start from 12. But maybe I'll get it started slowly, because if you really have anything to do before 12, then you might be late to the section, but I'll just get started from 12, okay, 10 to 2 p.m. Then we are going to review questions. Okay, yeah, maybe just background noise. So then we are going to review the past final exams. I'm going to post it past 3 years tonight, so final exams, and then you will see what's going on. And then, of course, the format is different. Maybe later on after this class, if we have time, I will pull out the final exam last year, and then you will see what structure is. And you also see some questions actually take home. That's the questions for students who want to redeem themselves. But in this year, I don't think I can give you any grade lower than P, which means you don't have to do any redemption at all this year. But I will still email you if I see your final, I don't like it in some way. I'll still email you to talk about in person to let you know that it's even though you will be able to pass this class, but in the master exam you possibly need to pay attention to something. I will do this kind of personal communication with you. Okay, and then the other review section would be on Wednesday next week from 3 to 5 p.m. And then we are going to review another year of the past exams. Okay. More likely, we will do 2019 on Monday and 2018 on Wednesday. Okay, so any question about the final exams? Okay, if not, then I'm going to finish our class about large sample properties of MLE. Okay, then I said, oops, hold on. I accidentally pushed the mute button. Okay, hold on. Yeah, come back. Sorry. Good. Okay, last time we talked about the large sample property of MLE. I said people like MLE because of their consistent estimators. Okay, when n goes to infinity, which means that is theta hat as MLE going to converge in probability to theta 0, which is your target parameter. Okay, And then also is that when n is large enough, MLE is going to behave like asymptotic normality is. Okay, so don't know about asymptoticity, but pay attention to what is the variance then. Okay, so that's time we're deriving the asymptotic variance is actually its inverse of information number, or we normally say it's the inverse of a visual information matrix. Okay, the way I say matrix is because of sometimes theta is not only about single dimension. Sometimes, for example, if you do a mu hat and a sigma squared hat, if your theta actually more than one dimension, then the information is going to become 2x2 matrix. Okay, good. But right now, as these classes, we just doing, I think more likely we're doing only single dimension. But in the future, if you're going on to do anything other, to do PhD study, for example, or in doing your real application of thesis, you will see a lot of things you're working on multidimensional theta. And in that case, MLE is still awesome. MLE is still really good in terms, as long as you can get it. And as long as n is considered very large, then the variance matrix as an inverse of visual information matrix then. Variance in the diagonal part. Okay, for example, mu hat and the sigma hat is a variance. As well as you have the covariance part. In that variance covariance matrix X. Okay, good. And then we also talk about it. Sometimes the target parameters is only about theta 0 or theta. We are actually interested to estimate about function of theta. It's called tau theta 0 right here. And then you know that learning from the meter number 1, if you want to, the target variable is a function of theta. Then what's the MLE of that function of theta then? Nothing but what? Function of the MLE. Okay? It's the MLE has the invariance property. So easy to handle. As long as I can write my target parameters as a function, easy to get parameter. And then you just finding that target parameters MLE, you just do that transformation of the easy estimated quantity. Okay, and then even further, it's doing transformation is nothing but what? It's nothing but delta method to derive the large sample properties of my MLE, of my target parameters. Then by doing so, you will know that is what? It's variance right here of the transformation is going to become what? So that's what we learned about. For example, X bar right here. Right? This is what we're writing down as G prime, then theta, then taking square, then square, right? So this is what we do when we learn about delta methods. We do need to find out G function. G function right here is a tau function. Okay? So then the variance is nothing but taking the first derivative of the G function and taking square. Exactly this guy right here. Okay? Of a tau function, then taking square. Okay? Then times the variance is a sigma square. It's original variance right here, which is inverse of visual information matrix or inverse of information number. So no wonder the right hand side based on delta method, if you're really working on a estimator of the function of the some parameters, then the variance it could be easy to write down based on delta method X. Okay, good. So then Of course, by delta method, you're requiring tau function is a continuous function. And of course, the first derivative of the theta 0 cannot be 0. Theta 0 cannot be 0. Why? Easy to see, right? If this guy is 0 right here, then the whole variance is 0. You don't want to working on some variances. You don't want to working on some distribution with variance is 0. Okay, it's a meaningless distribution. Okay, so then in a lot of applications, tau function could be easy to find a non-zero function. That's pretty trivial. Not difficult to find out one function which the first derivative is non-zero function. Then, okay, so we're talking about so-called asymptotic efficiency because I said looking at this term right here. Okay, nothing but Kramer-Rao lower bound you learn. Okay, so that tells you that whenever you can find MLE, then MLE is going to have that asymptotic efficiency, which means that it's the variance of MLE is going to reach the Kramer lower bound. Okay, Kramer lower bound again it's the lower bound of a variance of every unbiased estimator. Okay, then again it's MLE not necessarily unbiased. Some MLE is not. Some MLE is a bias estimator, but asymptotically when n goes to infinity, then MLE is going to converge to something which is so-called consistent, or saying that it's when n is infinity, it looks like unbiased estimators. Okay, not only there's a consistency, but also variance is going to reach in what? The lower bound is. Okay, so that gives you MLE a lot of advantages because we would know that it's when n goes to infinity, MLE is going to have a smallest variance among consistent estimations. Okay, so by typical language of call it, MLE is asymptotically efficient. Okay, good. Then based on different estimators, whenever you can derive their large sample property, more likely they are going to be large sample normality by two estimators. Then you can compare which one you prefer. Then it's not surprising to see which one have a smaller variance, right? Good. And then there's so-called such a term called relative efficiency. Really nothing but taking the ratio of the two asymptotic variances or limiting variances. Again, I want to mention one thing. It's you heard me saying before. I want to talk about one thing again. It's theta one squared right here. It's a variance of square root n, then t1n minus theta. Then when n goes to infinity, right? So you could lousy to say so, right? As a sigma squared. We could lousy to write so. Imagine that it's when t1n, when n goes to infinity, then the variance of root n times t1n minus theta is going to be similar. It's going to be similar to the sigma squared to it. Okay, but in terms of communication, our language was still saying sigma one square is a limiting variance of t1n. Okay, if you heard me to say so, I actually picture that it's times root n already. Okay, so when I say limiting variance of t1n, I'm not talking about limiting variance of t1n. Okay, I'm not talking about this. Okay, so because root n, if you root n, this is a magic number right here. It's if you learn estimations don't have root n convergence. Okay, then in that case, then we'll use different language to talk about it. Okay, but in the current level, we always have root n convergence. So reason why when I say limiting variance of t1n, I basically picture in the root n already here. Okay, So, but that's only about notation, right? It's about language things. But I want to emphasize that. Okay, good. About two limiting variance, and then trying to compare about efficiency. That means eventually just taking a ratio of two variants to see which one is smaller. Okay, so by notation, I think we'll put I think right here talking about this is your target. This about is a reference. Okay, so maybe this is like old estimator, and you are trying to find a new estimator right here. Okay, then you want to know that whether or not my new estimator is going to be better than old estimator in terms of computation. Then I think you put your new estimator's variance in the denominator and then denominator, and then you put your old variance in the numerator. Okay, so then which means that if you are really looking for something better than all things, then you're looking for your relative efficiency ARE is bigger than 1, because you are looking for your new guy right here have smaller variance. Okay, good. And then next time we stop right here talking about this is the typical example. I hopefully I can find something in the final exam actually. So not only about logistic. Okay, yeah, I think I possibly could find something right here. I can give you different scenario, and I give you different estimation, which are both are consistent estimation right here. Okay, so say x1 to xn is a logistic distribution whose parameter theta. Okay, so by the distribution, we will know that exi or ex1 is theta. Then variance of x1 is pi squared divided by 3. Okay, that's based on logistic distribution x. Okay, then I can write down my x bar, right? Okay, because okay, I'm going to use my theorem first. Then using my theorem, I'm going to apply what? Central limit theory. Okay, then I can get root n x bar minus what? Ex1, right? Ex1 right here. Then ES1, it turns out to be theta right here. Okay, and then by central limit theory, the variance part would be what? Variance x1, right? Variance x1, I said by distribution, this guy is pi squared divided by 3. So the first line of estimators is nothing but based on central limit theory. In the meantime, if you actually deriving the MLE of theta, you will find out that it's not x bar. Okay, even though I don't specifically solving of the what theta had it. Okay, I don't know what theta had look like, but by notation or by mathematical expression, I can still write down the MLE's large sample distribution, which is normality. And then you go back to that results I have, right? So I said right here, I do have a function number. So that means you need to find out what the PDF of the log. You need to find out the PDF of logistic distribution is, and then taking log, then taking second derivative to the theta, and then deriving expectation, then put minus on it. That's the definition of information number is. Okay, going through that, you'll find out is information number is 1/3. Okay, information is 1/3. That means inverse of information become the variance of the MLE, or the variance of MLE then becomes 3. You see what? You see I have 2 estimators. Both are consistent estimators of theta. But they have a different limiting variance. And then you will be compare which one having smaller variance, right? Then before doing that, you will imagine exactly one thing is the MLE is going to have a smaller variance. Okay, good. So which means that it's, if you really don't know how to compare their two numbers, you could just write down MLE. Right, you will get most of the points from me, and maybe just take 1 point away from you saying that you do not specifically to compare two numbers. Okay, good. But I get your idea. I know you understand that. That's good. That's good enough for me already. Okay, if you really want to specifically compare with that, as you can see right here, this guy 3 is from logistic. This guy pi square. Yep, 3 from logistic. 3 from MLE. Then pi squared divided by 3 from central limit theory. Then it turns out to be, of course, pi squared is bigger than 9, right? Because pi is what? 3.14, da 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 da. Okay, and then so they no longer ARE smaller. So which means that it's if your central limit theory is your new estimators, then you'll find out your new estimators is not stronger than MLE or something like that. Okay, so that means comparison between the comparison between limiting variance should be straightforward, but the key point is as soon as you can derive it. Okay, good. Okay, so let's move on to trying to talk about, hey, if I do have MLE having so much good properties, could I using that to further do any testing? Or could I using that to do any further so-called statistical inferences? For instance, yes. I mean, tricky enough, we have been teaching LR log ratio test, right? Lambda X. And then I also keep reminding you, as long as LRT, you should write down your definition, right? You could get a bunch of points. Right? So your definition of numerator denominator, it's like a bunch of points. And then what's the typical drill we'll do, right? The typical drill we'll do it. We are trying to say, well, LRT basically rejected the null hypothesis based on smaller values. And then I said it's, well, you don't know what distribution of lambda x. You don't know about the distribution of lambda x right here. So even though I do know that I need to using alpha, let me take out something right here. I want to work specifically. Okay. Even though I keep telling you it's okay, trying to find alpha right here. Right, on the null space, probability of lambda x smaller than c. Right? Right here that's how you find color of C right here. Right? Using type 1 error alpha to find color of C. And I keep saying one thing is what? As long as you know what distribution of lambda x right here, yeah, go ahead. Using a distribution to find color of C lambda. But I teach you what? I teach you saying it's a lot of times lambda x basically is really complicated quantity of statistics. You really have no idea what lambda x is going to distribute it like. Okay, hence, so such that lambda x smaller than c is not really useful. More useful is you are trying to find equivalent region of using what? Another easy statistics. Okay, and then whether or not bigger or smaller than some C star right here, depending on what TX you are using. And then by that, drawing a graph or drawing a feature, you'll find out which direction that would be as TX. And I said, usually, if you really don't know how to evaluate that, I say what? You should follow the direction, just follow what? Direction of the alternative hypothesis. Okay, good. That's a typical drill. And then, as you can see, we've spent a lot of time, especially in your homework, you just submitted. You find a bunch of things quite complicated, right? Writing down that specific lambda x's, okay? And then, since you guys know what's exact, what's asymptotic already, right? I keep telling you in my class, you need to tell what distribution, what kind of testing, what comes in interval is exact, what testing or comes in interval is asymptotic, okay? So the whole picture right here is what? We are trying to find exact distribution. So by doing so, what you find is exact constant interval, exact testing critical region. That's okay. And then you can imagine we pay so much effort trying to derive lambda x based on definition, finding C cutoff C, finding equivalent region, then finding cutoff C star. Okay. A lot of effort. It turns out to be you can forget about all this. Okay, you can forget about all this. Let me, pardon me, take out everything out. You can forget all this. Okay, right here. Not saying forget. One thing it's not really that easy to apply. Again, if you would like to assuming n goes to infinity, we can actually deriving the asymptotic distribution of the likelihood ratio statistic lambda. Right here, I'm going to tell you that I'm going to show the result first, and then come back to the proof. Eventually, you are going to show that it's okay. After collecting the data, you should be able to derive. You should be able to compute what lambda x is. Okay. Then you're taking log of lambda x, taking -2. Then that whole quantity asymptotically is going to follow chi-square 1. Okay, which means that it's you really don't have to write that equivalence anymore. You could directly using lambda x itself, then to do inference. But keep in mind, take log, take -2. You will see that later on. How do I testing right here? Okay. Then how do I know -2 log lambda x eventually is going to distribute it like chi-square 1 then? Okay, here's the proof. Again, nothing but tail expansion. Like I said, we don't use much of complicated mathematical tool. Okay, so you know what tail expansion is, right? But right now, if you remember, I do tail expansion to deriving the large sample property of MLE. At that time, I expanded of the theta hat around theta 0. But right now I'm going to do reverse. I'm going to expand function or log like a function around theta hat right here. Okay, then just follow what tail expansion is. This is first directive, right? L prime is nothing but score function, and then this is the second directive, right? And this is the third directive right here. Okay, good. And then by tail expansion, this is theta 0 minus theta 0 minus theta hat. Okay, then right here is what? I think I put minus. I put minus because of, so it should be plus. Okay, it should be plus right here. But right here, second directive, by definition of J, right? J is minus second derivative of log like a function. So there's nothing wrong right here to write down negative. Keep one thing in mind because I'm writing down J right here. Okay, I'm writing down the observed information right here. Okay, and then this guy is like this guy is the third derivative in expansion. But if you remember how I talk about right here, okay, theta star. So again, I want to say it again. So if you know that, pardon me on that. Okay, so I want to spend a little time on this. Again, it's if you don't write If you don't write theta, stop. If you really write theta hat, then there are remaining terms. Okay, good. By doing so, or you can either write by mean value theory. You could write down this guy is a star, and then say star is between theta 0 and then theta hat x. Okay, that could be save you a bunch of times to write a bunch of remaining terms. Okay, that's a mathematical notation. And if you think everything follows through, then you're going to talk about what happens to each one. Number one is, what happened to this guy? What is the value of u theta hat? Nothing but 0, isn't it? Because theta hat exactly you're solving using score function. When you do derivation, you're using that solution, you're using that equation to solving for theta hat. So score function of theta hat is 0. Okay, so because doing that, the whole thing actually gone. You don't have to worry about it. Okay. Then the target value is -2 log lambda x, right? So then by doing that, so I maybe need to tell you actually the null hypothesis is theta is theta 0. Alternative is theta doesn't use theta 0. Okay, by doing so, the lambda x, right? By definition right here. So let me write down here, okay, right here. Okay, by doing so, this guy nothing but what? Under null hypothesis, right? Supremum, right here, your numerator is what? Supremum under null hypothesis. Null hypothesis only have single points, so really nothing but plug in theta 0 x. Okay, then your denominator is supremum under overall space. Then there's no restriction, so you could just directly run theta hat. Okay, then you're taking log. You're taking log, right? Taking log become, so taking log become what? Taking log become log L theta minus log L theta hat x, L theta hat x. And that become, by writing, become L theta minus L theta hat. Okay, the reason why I can take L, then become logical function. And then remember this is minus right here, right? The inside guy switch. Okay, becomes 2 log theta hat minus L theta 0. Okay, so I think it's not really complicated, but in the following you need to pay more attention to. Okay, so it means from here, okay, from here, you can actually move what? You can actually move, okay? Not easy to see, but I want you to see that. So right here, move to this side, right? Then the left-hand side become L theta 0 minus L theta hat x, okay? But in the meantime, I have negative sign right here. So also move to the left, then become switch, then times 2. Okay, that's the reason why eventually you can write down right here. Okay, did you see that? Okay, then you're taking everything out of the square. Okay, so that means everything coming from this guy right here. So pardon me, I'm taking this out. Taking this out. So inside guy, so everything right here become this guy right here. Okay, good. So then I purposely putting out root n. Okay, you will see why I do that. And then also inside guy divided by root n right here. So really nothing but just moving the whole term to here, okay? And then taking square out, of course, inside guy can switch, right? Okay, because it's square term right here, so theta head minus theta 0 is the same thing as theta 0 minus theta head. They're all identical. And then by that easy operation, you could find this term right here become here. Okay, shouldn't be hard to see. And then right here, I just purposely writing down root n inside. Okay, and I put just a cubicle outside. By doing that, I basically creating root n then cubicle, root n then cubic, and root n then cubic. Then I need to compensate by 1 divided by n, then 1 divided by root n. Okay, so everything is for a purpose. Okay, I'm saying so it's you do need to evaluate because eventually I'm trying to show that minus 2 log x. Eventually I want to show that minus 2 log x goes to d, then chi-square 1. Okay, then that basically means that it's you carefully evaluate which one conversion to where. For example, right here. Okay, nothing but MLE root n convergence, and then this guy goes to D, normal 0. Where? What's the variance? Information number inverse. Remember that? Okay, that's for MLE. And then how about this guy right here? How about this guy right here? Okay, if you remember, let me put it right here. Okay, if you remember, say when n goes to infinity, right? So theta head right here is going to be consistent estimation. So the whole term right here eventually will be very similar to this guy, right? Then divided by n. Okay, so let me put lousy notation. I want to show even though I told you after you're writing down convergence to P, your right hand side don't have n. Okay, so this is lousy notation, but I want you to see what happens. First of all, is theta head goes to theta 0. Okay, then if you remember what the whole thing converges to, this guy eventually will convergence to P, then y1 theta 0 as well. Okay, good. So if I go to the slides right here, okay, so this is what I'm talking about. Okay, by weak law of large number. The j theta 0 divided by m is going to converge in probability to I1 theta 0. Okay, and then again, this guy right here, the converge to P, then expectation K1. Okay, again, because theta head right here eventually converge to P, then theta 0 as well. Because squeeze, right? Because theta head goes to P, then theta 0. Eventually, theta star between two numbers going to squeeze to that theta 0 as well. Okay, and then you know that this guy right here, inside guy converges to D, normality, then 0 something, normality anyway, right? So most importantly, it's this guy, you do have something converge to 0 because when n goes to infinity, then the whole thing going to come to 0 in P. That's important because eventually this kind of remaining terms, the whole remaining terms right here, as you can picture it, what you want to then goes to P, then 0, because the remaining terms is going to become really meaningless. Okay, contribute nothing when n goes to infinity. That's what you're looking for. Then key point is what's inside, right? So I said this guy is what? Normal 0 I1 inverse. okay? Then this one goes to P. Oh, I can take this out if you want a clear picture. This one goes to P. This guy goes to P, then I1 theta goes to P. I1 theta 0. Okay? So again, the same thing, right? What do I mean by same thing? What do I mean by same thing is this guy goes to D, convergent distribution. This guy goes to P, convergent probability, then times together, converge to where? Converge to D, right? And then what happens? What theory are you going to use to argue that what eventual convergent distribution is? What theory you're going to use? Nothing but Slutsky, right? Slutsky tell me that it's this guy is N, this guy is 0, and the invariance, this guy is I1 theta 0, then times inside. Okay, of course, pardon me on one thing, it's not actually I1 theta 0 because you do have square root right here. Okay, square root. Sorry about that. I should have emphasized that. There's square root right here. Inside guy converge to I1 theta 0, but you do have square root. So you do need to put square root on everything by continuous mapping theory. And then you will find out that it's, okay, this guy's square root I1 theta 0, then times in the variance becomes square, right? Then inside guy's I1 inverse, then compensate out, then become normal 0, 1. You guys see that? Okay, good. So you do want inside guy normal 0, 1. Why is the case? Because inside guy convergent distribution to normal 0, 1, then you're taking square. No wonder eventually this guy goes to D, then chi-square 1 is, because inside guy is normal 0, 1. Okay? Good. So really everything right here is what I said in order to eventually get convergence normal 0, 1 is. Okay. Any question on this? I know it may not be easy for you to go through it first time, but after this, you just sit down and look at each terms and then ask yourself, do I have any current theory to tell me that which item converges to which? Okay, either convergent distribution or convergent probability. Okay, then you do that evaluation. Eventually, you'll see that it will converge to chi-square 1. It's okay. Good. Of course, we show this. Not surprising to see if you're taking log, if you're taking square root, the left-hand side become normal 0, 1, but need to pay attention to positive and negative. Okay, that's a quantity. That might be called side deduction, but they're identical. So really, I don't use this quite often. Actually, I just to be sure that I just using chi-square 1. Okay, as the asymptotic distribution of the laboratory test. Okay, so again, what that's supposed to mean then? That means next time if I'm asking, saying it's deriving the large sample laboratory test, you don't need to find any equivalent. You don't need to find any equivalent region. Okay, it takes time to find out equivalent region, right? If you go through the homework, it's just a bit annoying, right? Although it's fun to operate because mathematical is interesting, but in terms of practical point of view, it's if you want to get a quick result, especially you have laplace function, you don't have to derive exact distribution of your laboratory test. You could just take in log, take in minus, and claim that is asymptotically they're going to follow chi-square 1. Okay, so that means laboratory test and you will see that it's later on it. Okay, the test region of laboratory test still that way, still this way, still this way. But whenever then rejection region -2 log lambda x right here is bigger than some color of C, actually. Okay, because it's taking -2 log on left hand side, then smaller become bigger than C. But right here, because you do know what distribution of the -2 log lambda x already, then C right here nothing but chi-square 1, then cut off is actually 1 minus alpha, again, left hand side. Okay, I will show you that later on, specifically writing down. Because at the time, you do know the large sample distribution of -2 log lambda x is. Okay, this is so-called laboratory test under null hypothesis, theta equal theta 0. In the meantime, you also having other choices. Maybe asymptotically, you don't need to do complicated deriving level functions. And another choice is called score test. Okay, score test. And then this guy is really using what? It's really nothing but using the properties of the score function. It's okay, so I can bring you back to the previous slides. We do deriving the large sample properties of score function right here. Oh, where is that? No, 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 right here. Okay, page number 8. Okay, so we do deriving the large sample property of score function. Then we can actually using that to develop a test. So which means that it's as long as you put your I1 in the left hand side, right? Then that become 1 square root of u theta 0 divided by I1 theta 0, then taking square root, of course, right? You're taking out the variance, it becomes square root I1 theta 0. Then it will become to D, then normal 0, 1, it's right? Not surprising to see that. Okay. Since that guys are normal 0, 1. Since you told me that it's under null hypothesis, theta 0. So eventually, I could use this quantity to do testing. Okay. So right here, I just purposely put root n in the bottom, right? Then become n times I1 theta 0. And you know that, right? You know that I1 theta 0 is n times of information number, then become the total information, In theta 0 is. Then because the asymptotic will follow normal 0, 1. Later on, you will see that it's a critical region of score test. Really nothing but using that theta 0 divided by square root In theta 0. This guy right here. Bigger than what? Say Z1 alpha over 2, it's right here. Okay, good. So because that quantity inside guy right here is normal 0, 1 asymptotically, so I can just treat it, picture as a normality. Then introducing normality is cut off, right? Okay, so similarly, I also told you that it's root n times theta. I also told you that it's MLE's asymptotic property is this normality 0, I1 inverse. Keep that in mind. Again, for score function, variance is I1. For the MLE, the variance is I1 inverse. Okay, so using the same logic, right? So I can also pull my variance to the left hand side, then become root n, then theta hat minus theta 0, then divided by square root I1 right here. Okay, goes to D, then normal 0, 1. Okay, good. And then it's become so-called word test. Word test. So it means score test. So Lagrange test using Lagrange function, score test using score function, and then word test using MLE. Okay, and then but you do see different version of word test. It's because of I can handle different things in the denominator. Okay, so right here, one thing is what? I plug in theta hat right here. I plug right here. Okay, although in denominator, I can write down I1 minus theta 0. Okay, but sometimes people plug in theta hat into theta 0. Okay, and then of course then it becomes to the first one right here. First one right here. Okay, or people were saying that it's, hey, if you could do that I1 and I1 theta hat right here. Okay, so that means the first term, let me put it here, maybe it's too busy right now. Okay, so what I'm trying to say is this. So if you could put, say, so ultimately is this. So let me write them again. Everything is based on root n theta hat minus theta 0. Let me pick bigger. Everything's based on the same property. Square root I1 inverse theta 0 goes to D, then normal 0, 1. Everything's based on this. Okay, then based on the large sample property MLE, then you could do like what? I1, right? You could put on the top, right? I1 inverse become I1, then theta 0. I could write so as well. Then different forms of the word type test, all based on how you handle the variance part right here. Okay, the first one we talk about. The first one we talk about right here is what? Nothing but plugging theta hat into theta 0. That means I'm going to using this guy as the variance. This guy still goes to D, then normal 0, 1. Okay, why is the case? That's because of what? Slasky. Okay, as long as you plug in something convergent P right here, as long as you plug in theta, let me see. Let me write more specifically. As long as you plug in something consistent estimator right here, then by Starsky, that one still distributed like a normal 0, 1. If you remember that when we talk about the Starsky theories, okay. And then since doing that, then from here to here, the second variation, the second version of word type test right here, okay. Also not surprising to see it. I can actually write down n times I1. I can actually write down what? In, right? Theta 0, theta hat minus theta goes to D, then normal 0, 1. Then people would see that it's, hey, maybe I can using what? This is expected information. People would say, how about I plug in observed information then? Okay. Then even further is what? I plug in theta hat or theta 0 into a variance part. They are all normal 0, 1s. Okay. So in practice, everything should be in practice, everything should be identical. Everything should be asymptotically identical because of large sample properties. Okay, large sample convergence things. Okay, so which means that it's, in terms of word test, there are different forms you can work on. Okay, so this guy possibly a most common form people will use right here. Everything in terms of variance, everything is based on observed data to estimate the variance as well. Okay, but if you insist to do any other variations, it's also okay as well. Especially here, it doesn't matter at all to me which one's actual or type test or word test. Okay, so let's just specifically go to Bernoulli case, right? So the whole page right here at the right before, so I'm going to skip that. Nothing but really x1 to xn Bernoulli, then write down likelihood function, write down score function, write down observation matrix. And then in order to do every testing, you do need to deriving every respected or corresponding quantity. It's, for example, information number, you do need to derive it, right? So then if I give you null hypothesis theta 0, alternative theta doesn't equal theta 0, okay? Then based on 3 tests, actually just, looking at your cheat sheet, right? Looking at your slides, you know how to do it. For example, the number one is what test based on what? Based on MLE. And then this is MLE's property, okay? By deriving in this page right here, you know every quantity of them, okay? Then such that you can write it down based on that large sample property of MLE. And then right here, right? Again, really putting down I1 to left-hand side, right here. Okay, so by doing that, right here, again, it's I1 is theta times I1 inverse. I1 inverse. Right here is theta times 1 minus theta. Okay, right here. We derived it that before. And then really here, just nothing plug in, right? Plug in theta hat, prime theta hat into where the theta 0 is. Okay, such that eventually this is a quantity. This is a quantity you're going to do testing. And because asymptotically they are normal 0, 1, okay? Of course, when you do a testing, you're using 2-tailed test. Each one just reject it, right? Either too big or too small. Each one having an alpha over 2 in terms of Z quantile. Making sense? Because of asymptotically, they are normal 0, 1s. Either too big, either too small are rejected. Then how about score test? Again, using the large sample property of a score function, it's okay. Eventually, this quantity we talk about, okay, divided by n1, ni1 theta 0. Okay, good. So if you insist, saying is, could I plug in theta here right here? I'm saying it's okay. Okay, but it's not regular definition of score function. But if you do that, I mean, I cannot say it's wrong. And then again, they are all asymptotic equivalent. So, but by common approach, we just using theta naught for score test, and not how to see that right here. It's n1 and ni1 then become in. Okay, then right here it's just plug in what I1 is from your derivation of I1 theta is, and then eventually become less. Again, it's this guy asymptotically would become normal 0, 1. So intuitively, do testing is 1. You have in their absolute value, either too big or too small, like a normality. It's the same thing as the word type test. It's okay comparing to the your normal 0, 1's quantile. And then LRT, you just need to calculate in that -2 log lambda x. Okay, then based on this, you do have right here, right? You do have this guy, you do have this guy right here. Okay, you're taking taking -2 log lambda x, eventually compared to chi-square distribution. Then keep one thing in mind, it become bigger. Okay, not surprising, right? Because you do have normal 0, 1 right here. You do have testing based on normal 0, 1. You're choosing too big or too small, okay, to reject your null hypothesis. Right now, your chi-square 1 is taking square of a normal 0, 1 is. Then too big or too small, taking square or become too big. Okay, so it's not hard to imagine what this guy right here is bigger than some quantile edge. Okay, again, this guy would be the same thing as a normal 0, 1 quantile, then taking square, right? Become chi-square 1's quantile. Sounds good? Okay, good. So this guy right here is actually calculating the numerical example, which means that is I just specifically told you that is what the theta is. Then I also specifically told you that what n is, what summation, what data is. Okay, summation xi is 3, what data is. And then using that, I can calculate MLE. And everything is plugging back to the derivation I have for you right there. And you will find out it's this guy is chi-square, this guy is LRT statistics, this guy score statistics, this guy word type test statistics. Okay, they are all very close. Okay, and then hopefully they will get the same conclusion. Everything is non-rejected right here. Okay, however, I cannot guarantee you every time you see there 3 testing having consistent results. Okay, or saying that I cannot guarantee that 3 tests is going to have the same conclusion, especially if your sample size is not large enough. Then you might have having that difference between different tests. Okay, so I'm going to draw one graph. It's which every time I teach you this, I'm going to draw. Okay, so say if you're collecting data, okay, and then this is like your LIGO function. It's okay, and then where's the MLE? Your MLE is this. This is pick right here. This is your MLE right here. Okay, so by dot 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 right here, dot 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 right here, you would have in that dot 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 right here. You having this guy right here is what? Your log LIGO function values. Okay, say if your true null hypothesis, they are 0 right here. They are 0 right here. Okay, then you will have in there right here, right here, it's your log value of the theta 0 under null hypothesis. Okay, good. So if I told you that this is exactly how you do word test. Word test nothing but how far away of your theta head and then theta 0 is. That's your word test. Okay, could you tell me where is the log? Could you tell me which one is lag ratio test? Lag ratio test is nothing but what? The difference between lag ratio, like a log LIGO function is, right? Good. So this is where the lambda is. That's where -2, or that's where the log lambda x to tell you. So this is LRT is. Okay. Based on this graph, could you tell me where is score function? Okay. Score function is derivative of log LIGO function. That means this is based on theta 0. This is the slope is your score function ux theta 0 is. Okay. Then if these two guys are really close, if theta head and theta 0 are so close, you don't reject the hypothesis. What does that mean? That means your LRT in terms of difference between log LIGO function also very close. Okay, so that make that is the same sense of why I say asymptotically they are equivalent, right? Because if your null hypothesis is actually true, theta head is going to close to theta 0. You will say that you will log theta head, log L theta head also close to L theta 0. Okay, then what happens to your U theta 0 then? If they are so close, the line, the slope right here become what? Would be really flat. the reason why your score test actually testing against 0. If you see that form of score test is right here. Score test right here. Okay. It's actually minus 0 right here. Okay. So using this graph, you understand where the word test is. What does word test mean? Then where LRT is, what does LRT mean? Then where the score test is, then what does score test mean? Then you understand what eventually, if your null hypothesis is actually true, and then when your n goes to infinity, then all 3 tests are equivalent. Making sense? Any questions about a symptotic, about limiting, about a symptotic test? Okay, I don't have chat to say questions. Okay, then final one would be this. So could I actually do interval estimation? Okay, especially is what? Because I do have 3 testings. Because I do have 3 asymptotic tests. Then based on the converse interval we have been learning, we can always invert a test to become converse interval, right? The same logic is actually applied. Okay, good. So that means you just need to pick up all these test regions. Okay, and then writing down that theta 0, and then eventually bring your eraser, right? Taking out theta 0s. Okay, take out theta 0s. Then your 5 converse interval right here. Okay, so these 3 guys are all based on what I derived right here. Right here, right here. Sorry. Right here, right here, and right here, and right here. But keep in mind, this guy has to be theta 0. It's not 0.5. Okay. Replacing every 0.5 in that 3 lines to become theta 0, you'll find the same thing right here. Okay, good. And then let me ask you one thing. Imagine that. Okay, so even though this is acceptance region, eventually I still need to put my theta 0 or theta. Okay, it doesn't matter, right? The same thing. Eventually, I still have lower bound, upper bound, right? This is what converse interval means. Okay, so even though I give you the result directly right here, let me ask you one thing. Is that easy? Is that easy for me to put theta 0 in the middle, having that lower bound and the upper bound writing down based on LRT? Look at this. Let me take out this. Okay, I want you to look at it right here. I want to look at this. Is that easy for you to isolate the theta 0 in the middle with lower bound, upper bound? No, right? Okay, this is log right here, and I have log theta. I mean, this guy log 0.3 and minus log theta. It's not apparent theta 0 for me to do operation. Okay, the answer is yes. You cannot put theta 0 in the middle doing easy operation. But does that prevent you to find any value between lower bound and upper bound, then satisfy the whole inequality? The answer is yes. You could do any searching, any numerical approximation methods, trying to find this lower bound and this upper bound between these 2 guys right there. Every point between these 2 guys satisfy the whole inequality. Then you got it. Okay. Then to this kind of score function right here. Okay, score function right here. The same thing, right? It's not easy for me to do operation to put theta 0 in the middle to find my lower bound, upper bound. Yes, but I can still do some research, right? Or some kind of numerical searching right? To see which value of lower bound and which value of upper bound, then between them satisfy this inequality is. Making sense? And then some of you may tell me it's, hey, could I do this? Could I actually replacing this guy X bar, this guy X bar as well, such that I can put my theta 0 in the middle pretty easily? The answer is also yes as well. Okay? So which means that it's as long as you would like, assuming my sample size large enough, then plug in X bar right there. If you get your life easier to put theta 0 in the middle, you don't have to do any programming to searching for solution. Go ahead. Okay? That one still 1 minus alpha comes interval. Okay? But again, this testing are based on asymptotic results. So everything you find is what? Asymptotic constant interval. Okay? Then you have a different version of asymptotic constant interval. Okay? Good? So the final point right here, final slides. You do have that x1 to xn. You can basically using the exact interval, you could derive that. Again, these three guys are based on asymptotic results. Everything based on asymptotic results is asymptotic interval. It's approximated one. In this particular case, you can actually finding exact interval using CDF methods. It could be a good example for final exam. Okay, I might actually give you that to ask you deriving asymptotical interval or as well as exact constant interval. Okay, but then you need to pay attention to what the difference is. One is exact, one is asymptotic. Okay, then you have using a CDF methods, you have that interval, this guy right here. And then you'll be curious which one looks like more optimum or which one actually have a shorter length, right? Something here will easy to calculate which one with shorter length. By my eyeball testing, I cannot see which one is smaller, okay? But I think they are really close. So it's really, there's no really obvious difference between these 4 guys. Okay, good. Okay, I finished my teaching everything for the final exam. Okay, so I want to thank you for your involvement, for your work to this class. I know the things have been difficult. Oh, one more thing I want to mention is, of course, I want to wish you have a good summer. Okay, right here. Hopefully you can see what I want to try to point out right here. Okay, so in the final, everything right here, every testing right here. Let me see. Okay, hopefully I have this 2 minutes, right? So let me pull out exactly the form of the, okay, so testing right here. I'm going to take a lot of things out. Okay, I meant to say it. Every result right here is based on IID data. Okay, but in the final, I may give you independent but not identical data, like meter number 2. It's that Poisson regression question right here. So if you don't have IID data, you only have independent but not identical data, does this guy still hold? Yes. Only thing you need to change is, look at right here. Don't put it down as n times I1. Okay? Writing using information, total information directly. Okay? For example, because it's not IID, but because it's independent and it's independent but not identical, you could still write down your likelihood function, isn't it? Right? Regression is to write down likelihood function, and because you can write your likelihood function, so there's nothing can stop you to do LRT. Right? Based on likelihood function, I plug in theta hat, plug in theta 0, and do testing. Easy. But in the school function, you do need to pay attention to, because it's not ID, individual information is not identical anymore. So you cannot write n times I1. okay? Because each I1 is different, but it doesn't prevent you. I can write down total information right here, IN, okay? The same thing happened to word test. You could always write down right here as well. I can write down IN theta right here. If you don't have ID data, you still have total information become your variance, okay? Right here, straightforward, right? Observe information based on your total likelihood function. Based on likelihood function itself, is you can derive in observe information. Okay, you will see that in the 2019 final exam as well. In the final question of 2019 final exam, you don't have ID data, but this guy's really not hard to adjust a little bit, not big adjustments. Okay, any questions? Okay, not a question, but a personal. Okay, yeah, good, great. So I do need to go because I do have a meeting at 2. Okay, hopefully I will see you guys in person pretty soon. Okay, again, I don't like online teaching. I don't like. I want to see you guys' eyes to know how you guys learn. So, but well, hooray, right? We go through. Okay, this is final class. Then if you have time, come to the discussion sections, review section next Monday from 12. Then we can go through exact questions, and then you guys would get better feel about what the whole semester means. Okay, good. Any questions? Okay.
I have a question about.
Yes, of course. Yeah, go ahead.
What about the remaining slides, large sample ML-based method 2?
Oh, that, yeah. Thank you to mention, yeah, Owen. So, yeah. That 1, 2 means that's actually more complicated one, but the principle wise is not different, but the dimension get larger. And then you will see bunch of applications actually based on LRT, and a lot of applications based on large sample theory. Okay, then I meant to including that it's I want you guys to see that, and then to get a feel about what real world is. Okay, in 1, it's still based on theory, not that actually applicable, because you don't, well, you still see some t-testing, I think, possibly in the future, but I just want you to let you know that don't be scared. In the future, if you do have a new problem at hand, don't forget about you always have MLE as a weapon to do some inference. But maybe you can develop even more awesome tools, that's for sure. But you still having some like basic tools. Then that MLE, the second unit is meant to told you there are a bunch of applications that actually based on the MLE's inference. Okay. Making sense?
Yeah.
Yeah. So if you have interest, if you have any interest to look at that slides, if you have any questions, just let me know. Okay, I can go through the slides with you if you do have questions on that. I also including Bayesian slides in the class units. Again, if you guys are interested in Bayesian, then that's an introduction, actually really like a baby stuff of the Bayesian inference. Okay, anything else I want to cover? I can cover for you. Okay, then have a good summer. Okay, good luck on final exams. And then between here and the final exam, don't hesitate to let me know if you have any questions. Okay, so you know I'm always accessible. So then if you do want to understand something, you just let me know. Then we can working on the slides, and then you will see. Again, statistics is really easy. I mean, I really cannot imagine what people not understanding statistics. Because statistics everywhere in your life, right? So, I mean, as I always said, it's I understanding statistics. So are you? I mean, even I can understanding statistics. So you guys should be better than me. Okay, good. Okay, then I'm going to close out because I really don't want to into a meeting. So then again, it's just let me know if you do have any questions.